you can really follow my video description, follow it and do the tests. So here, hypothesis testing. Hypothesis testing is all about statistical significance. And let's look at an example. A company offers a 10-lesson program of study to improve students' SAT scores. A survey is made of a random sample of 25 students. 25 students, scatter plot improvement in total SAT scores versus number of lessons is as follows. Look at here. Lessons 0, 1, up to 10. So up to 10, you have 10 lessons. And here are the improvements. What do you see from this scatter plot? Do you see any relations? What would be the relation? Yeah, Alex, you remember? You can see eyeball this graph, scatter plot. What kind of correlation do you see?
It has a pretty strong correlation. It's positive.
Yeah, strong positive correlation, right. And if you look at the computer analysis, dependent variable, improvements, predictor. So eyeball this output. Can we get a formula? Let me get a word file going. What would be the regression formula? Regression formula. Try to format. So regression formula would be a predicted y a plus b x. You need to get a and b. What will be a and b? Where do you find a and b? I'm going to replace a and b with a number here. Where do you find a? Lesson, how many lessons you take? This is a predictor variable. And you have a constant. The constant is, what do we call the constant? This is an intercept. So here, this one is a slope. Basically, A is negative 7.718. Here you replace this one, negative 7.718 would be B. B is the number of lessons, that's 9.285. 9.2854. X should be the number of lessons. Y would be a predicted improvement. Yeah, so here's a B. The B is a slope. If you look at the slope is pretty steep. As the number of lessons increase, the improvement increases too, and in a pretty rapid slope. So that's a regression formula you get. And then here's R squared. What is R squared? R squared give you percentage 89.1. 89.1. This percentage explains the amount of variability. You see, some of the people improve a lot. Some of the people don't improve that much. And there's a lot of variability among these people. Of all this variability on the improvement, what percentage can be accounted for by the lessons? By the number of lessons they take, what percentage for the differences in improvement can be accounted for by number of lessons they take? And that is 89%, almost the 90%, almost the 90% of the improvements can be accounted for by how many lessons you take. That is the meaning of R squared. And remember, how do we get the R squared? You get the correlation coefficient. Correlation coefficient and square it, you get the R squared. Yeah, so that's how you analyze the printout. The residue, this is the residue plot. What is the residue plot for? The residue, the middle point is 0. And you have positive residues and negative residues. Remember, how would you calculate the residue? The residue is the observed score minus the predicted score. The observed minus the predicted. And when you have a positive residue, that means the observed score is larger than the predicted score. And you have an under prediction. Your prediction is under prediction, smaller than the observed score. When you have a negative residue, that means you're over predicting. Your observed score is smaller than your predicted score. And then you plot the residue of all those data points. See how many data points do we have? All these guys. And you calculate the residue for each person. And you plot it here. What are you looking for? You're looking for patterns. Do I have a pattern going on? If you have a pattern going on, and then the correlation is not completely linear. If you don't have a particular pattern, it's just random. And then that means the correlation is pretty much linear. Here we don't have a whole lot of a pattern. See, the dots are all over the places. So that means the correlation is mostly linear. It's mostly linear. We don't have a lot of curvy correlation going on. Here you have a histogram of the residues. Let's look at a question. What is the equation? What is the equation of regression line? Yeah, we just figured it out. We figured it out. Yeah, predicted improvements. This will be the predicted y, little hat here, the predicted y. Improvement, I should write predicted, but that's okay. I got a hat here. Equals to a negative 7.18 plus, this is the slope. This is a intercept, the slope. All right, you got the predictive formula. And then what's your interpretation in contact, the slope of the regression then? Basically, you want to interpret this number, the slope. Uh, Slope. What is the meaning of the slope? The lesson, first of all, the slope, you see, is positive. It is positive number, and that means as the number of lessons you take increases, your improvement or your predicted improvement would also increase. That this is the meaning of the positive sign. Increase by how much? As if you take one more lesson, remember there are 10 lessons altogether. If the number of lessons you improve, you take increase by one, taking one more lesson would lead to a 9.2854 units of improvement in your predicted improvement. This is a slope. The slope of regression line is 9. Yeah, this one, 9.28. That means on the average, each additional lesson, if you take one more lesson, is predicted to improve your total score by 9.2 units. Yeah, that's the meaning of the slope. Yeah, how about this one, the constant? The constant is intercept. Here, the intercept is your predicted improvement if you're taking zero lessons. If you don't take any lessons, you're predicted. So if this here is a 0, and then this part is all gone, your improvement is going to be negative. That is what happens. It's predictions. Prediction what happens if you don't take any of those lessons. Interpreting the slope. And then R squared. What is R squared? R squared is a correlation coefficient squared. And from the R squared, you can calculate the correlation coefficient. So what was R squared? 89 point, yeah, let me write there, 89.1. R squared 89.1%. So that would be 0.891. These are equivalent. And then from this information, we can get the correlation coefficient. Correlation coefficient between the two variables. Let me grab my calculator. Right, if you know the R squared, you know what is the correlation coefficient. So this one would be the square root of 0. In one, you have to turn it into a decimal in order to get the square root. Let me go get the square root. Here, square root 0.891, 0.94. That is very strong positive correlation. And then we talk about the interpretation. There's a reason that the R squared is given as a percentage. This means 89%, 89.1% of all the variability in improvement is accounted for by how many lessons you take. Yeah, so it's 81% of variability differences in the improvement can be explained by or accounted for by variation in the number of lessons you take. Yeah, here they do want you get what is get the value of correlation coefficient, right? Yeah, we just did that. Square root. And then perform of a task with significance, slope of the regression line. Yeah. You want to do the significance on the slope. Here, this is the slope. Is it a significance? Is it a statistical significance? And then let's do the hypothesis testing. Hypothesis testing, we start with two hypotheses. One is called let's start with the null hypothesis, which is the research hypothesis. What would be the null hypothesis? Slope is 0. Beta, yeah, I don't have a beta here. See if I can copy a beta. The slope is beta. Beta is 0. And the alternative hypothesis is beta is not 0 and equal to 0. We don't know whether beta is larger than 0 or smaller than 0, but it's just not 0. A beta equals to 0. What be that like? A beta equals to 0 would be a flat line, horizontal line, no slope. And this one, if you eyeball the slope, it's like a 45 degrees. It's not 0. It's really not 0. But the hypothesis says it's a 0. You try to use this evidence to reject the null hypothesis. How do we do that? We have the research hypothesis, and we have the null hypothesis, and you need to here, so you get a t-test. So actually, the computer output always gives you the t-test result. If you look at the computer output, the t-test, here is a t for the slope. T for the slope, t for the slope is pretty large, 13.68. So how do we get the t? How do we get the t value? Remember when we were the slope we observe, this is observed value 9.285. Here we observed the slope based on the people we tested is 9.28. And the null hypothesis is 0. So you calculate the difference, between what you observe and 0. And you divide it by the estimated standard deviation. The estimated standard deviation is here, 0.6789. And the degree freedoms altogether, you have 25 people, and minus 2, that is degrees freedom. So here you have the t value, and the p value, it's eyeball the p value, 0.000. What does it mean to be statistically significant? A statistically significant result would have a large p-value or small p-value. Remember that. If a test is statistically significant, would you have a large p-value or small p-value? You would have a small p-value. The p-value would be smaller than 0.05 at a minimum. That means the difference between the observed value here, 9.285, the probability that this difference, 9.28454, occur by chance is smaller than 5%. Very small, very unlikely that this big difference in the 9.285 is produced by random chance. So it's probably not by random chance, If not by random chance, it's more likely to be produced by how many lessons you take, how many classes you take. You want this number p-value to be small in order to have a significant result. And you eyeball this p-value. This p-value is smaller than 0.05. So it is indeed statistically significant. Yeah, it's all about reading the chart, reading the graph, getting the information. And let's look at another question. The following table gives a serving speed. So this statistic task is kind of reading intensive. It's reading intensive in that you need to understand the questions. And the questions are very applied. Some of them about sports, some of them about machineries, some of them about cars. So you got to really understand what they're talking about. Speed, serving speed, cannibal serve 10 randoms professional. Oh, this tennis players. And they're testing a new tennis racket. All right, old racket, new racket. How many people do we have? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm missing one. So where's the other one? Yeah, I'm still missing one. Okay, there must be one more, so that's okay. Uh, is there evidence of straight line relation? Straight line, that's a linear correlation. Linear correlation with positive slope between feeding speed and the new racket. So you want to see if there's a relationship, a straight line linear relation, positive slope between serving speed of the professional old new racket. Yeah, so you have two variables. One variable. Let's see how come I don't see this one. I don't see all the numbers. There might be a display problem. Uh, is there a relation, strong linear correlation between these two numbers, old racket performance versus new racket performance? So you have a scatter plot here. You see a straight line. You do see a straight line. Strong linear correlation. Residue. No apparent pattern. When you have a no apparent patterns, do you have a linear correlation or not a linear correlation? When you don't have a pattern, when it's just random, like a ball, you know that the relation is mostly linear. When you do have a pattern, like when these dots line up in a straight line or in a curve, then you don't have a purely linear correlation. You would have some non-linear correlation. This is mostly linear. Distribution of the residue is approximately normal. So you can do a check. Yeah, do a histogram check on the residue is normal. And then, yeah, normal probability. Yeah, this one's not necessary. Yeah. And then you get, yeah, remember the calculator. I would highly recommend the TI-84, Texas Instrument 84 is really good. And then you can get the formula, This will be the regression formula. Regression formula, the predicted variable, also called the dependent variable, is a new speed. This is predicted speed. Predicted speed when you are using the new racket, and then the old speed. That is the speed of your serving using the old racket. Here, the slope is indeed positive. The slope is positive, and 0.99. The intercept 8.76. And then give the t value. T is 5.53. P, that's a probability. This is a key value for statistical significance. You want this p value to be smaller than 0.05. That means the t-test is statistically significant. Statistical significance. That means that you have a strong evidence to reject the null hypothesis. What would be the null hypothesis? The null hypothesis says the slope is zero. The slope is zero in the population. In the entire population of all athletes, the slope is zero. There's no improvement from the by using the new racket. But here your observation is no, it's not zero, and your evidence is strong enough to reject the null hypothesis. So you do reject the null hypothesis. Yeah. How would you interpret the least square line? Least square regression. Your least square regression has a intercept and has a slope. In interpreting your regression formula, you talk about the intercept and also the slope. What is the intercept and the slope mean? Yeah, it's almost one. So let's see. Uh, it's almost like one. Yeah, where? I'm gonna. Oh no. Question. No, else missed something. Yeah, here it is. Yeah. So you want to make an interpretation of the intercept and the slope. The slope, this one means this 0.99, 0.99. And you're timing it with an old speed. This means that those players who is really fast, who is faster using the old racket, will be also faster using the new racket. For each unit of increment on the old speed, you will see 0.99 unit of improvement on the new racket speed. That is what this number means. And this intercept means that when the old speed is 0, what happens with the speed using the new racket? The slope is approximately 1, it's almost 1, and intercept is 8.76. Regression line can use new racket increase ceiling. Yeah, right. So basically, even when the old racket speed is just an average, and then you still get an improvement of 8.76 by using the new racket. Player with lower and higher racket speed, yeah, good. That's what it means. So that's all about the course materials. These are all the materials that we have covered. And we are ready to do the tests. We're ready to do the practice tests. For the rest of the time before you take the exam, do as many questions as you want to. Do as many questions as you need to. Do as many questions as you can. So let's get some tasks going. I would suggest you start from the book. The book has 6 set of complete questions, 6, and you should do all of them. And you should keep track of what of your performance. Let's start with diagnostic test. Start with diagnostic test. All right, for the real task, you have 40 questions, 40 questions on the module twice, and then also free response questions. Let's look at this one. It is estimated. Let me copy this one. Diagnostic. Diagnostic one. It is estimated that 56% Americans have pets. However, favorite pet choice differs by geographic location. Random sample pet owners across classified by geographic. So you have pet owners and geographic locations. The result is in bar chart. And result in the bar chart. Let's see here. Oh, it's not really showing all the. Oh, here got all. All right. Which of the following is incorrect conclusion? Incorrect conclusion. Uh, yeah, I might want to copy this guy to look at it in the same screen. Let me copy this guy. All right, let's copy this guy. You eyeball this graph. This so two data, two variables. What are the two variables? One variable, different types of animals, cats, dogs, others. What kind of variable is this one? Categorical or numerical? Quantitative or qualitative? Qualitative variable, not numerical or quantitative. The second variable will be location, north, south. And this would be also a categorical variable, two categories. And then what I look at what are the conclusions. Oh no, I need to yeah, one more pets, look at A, more pets owners in the south than in north, answered other. Would that be true? Which one of it is incorrect? So more owners in the south than the north answered other south. Will this be correct? Is this correct interpretation or conclusion based on the graph? These are percentages. Or both two bars would add up to 100%. This is correct. Higher percent of south people from the south says, oh, other. What is the other? This is a other. That's good. We don't choose this one. Next choice says, twice as many pet owners in the south answered dogs than answered other. Where do you look? This one you are going to look at the north, only the north, twice as many as the dogs than others. Dogs, others. Seems to be true, right? Roughly twice. This bar is this section is large, almost twice as large as people who answered other pads. This one is a good conclusion, so we don't choose this one. Same number of pad owners in the south answered cats. In the south as answered other. Same number pads in the south. So now we look in the south. Cats and other. Cats here. Yeah, this seems to be true. These two segments to be seems to be equivalent. We don't choose this one. In both north and south, the same proportion part owners answered dog. That is the case. So we are comparing south and north dogs. Are these two proportions the same? Yeah, they are rather roughly the same. Last one, a greater proportion part owner in the north than in the south answered cats. North, greater proportion people in the north. Where are cats? Cats are here. The greater proportion pet owners in the north than in the south answered cats. Yeah, the proportion cats. Yeah, this seems to be good. So A, B, C. Yeah, I must have made a mistake. I must have made a mistake somewhere. One of this is incorrect. So E is correct. Let's start from this one. More pets only in the source than in source other. Oh, that's a tricky one. Yeah, this one is not right. What is the problem? More pet owners. More means number. More pet owners in the south. Yeah, why is this a problem? We know the proportions. So these graphs, these bar charts are proportions. Sample, right, but not numbers. Yeah, that's a problem. It's a percentage measure, not counts. These are not counts, these are percentages. We don't know overall how many people come from the south in the sample. We don't know how many people who come from the north. Yeah, this is tricky. Yeah, we don't know the numerical value. So this one is not good. How about the B? Twice as many owners in the north. Yeah, so this one is good because we are comparing within the north and we are comparing proportions. The proportion will tell you twice of them, say cats, twice than as say others. This one is good. This one is not good. Same number of pet owners in the south as the cats, right? Now this one is good, although it says numbers. Cats and other. We know that the same number and the same proportion of people from the south, like cats and others. In this case, we know both the proportion and we know the number because the total number of people in the sample will be the same in the south. Yeah, this one is about proportion. Good, good. So this is good understanding, a good question about proportion versus counts, proportion versus numbers. Let's look at number two, question number two. In a linear relationship, is there a linear relationship with calorie? Calories are sodium content of beef hot dogs. Random sample 20 beef hot dogs give the following regression output. So you have 20 hot dogs. That's your sample. And you know you have two variables. Calories, that's one variable. Sodium. So that is output. And let me copy this one. Yeah, we just talked about this one, right? We were talking about a regression. Dependent variable sodium, predictor variable. You are trying to predict sodium from calories. Maybe the more calories this hot dog has, the more sodium it contains. Which of the following give the 99 confidence interval for the slope of the line? Yeah, so you got to look for the slope, And how do we figure out the slope? We got a couple more choices on the other page. Okay, here. Copy this one. "99% confidence interval." 99% confidence interval. You have several choices, A, B, C, D, E. And where do we find the slope? So we got to figure out the formula, figure out the regression formula. Let me add something here. Add a space. So predicted y minus letter hat predicted equals to a plus b times x. I want to replace a and b. Predicted for, so predicted sodium. That's a salt, basically. Salt is a sodium. Equals to where's a? Where's a constant? Negative. Negative 2 8.33. This one is a. A is a intercept, and plus, where's a B? B here, calories, 4.0133, yeah, times sodium. Sodium is X, sodium level. Oh no, that's sorry. That is times the calories. Yeah, calories is a predictor variable, And you want the 99%, 99 interval. 99 interval, what is the 99 interval? 99 interval on a t-test. On a t-test. And you got to figure out the boundaries on the t-test. Yeah. 99%. Once you have 99%, you know that you are going to use a curve. Which curve would this one be? This one would be the t curve, t distribution. T distribution, let me write it here. A t distribution, you need the degrees freedom. For this one, degrees freedom would be equals to how many people you are, how many items you have, 20. 20, and there are two variables, minus 2, that is 18. So degree of freedom is 18, and the confidence level is 99%. So it's 0.99. Sorry, 0.99, 99%. 99%. So we got to look at the t distribution for the cutoff. Yeah, where's the t distribution? Yeah, t distribution critical values. The t distribution give you here one-tailed, give you the area to the right of the cutoff. The probability is only one on one side, but in your confidence interval calculation, you want it in both sides. 99% confidence interval is in the middle. In the middle, you have 99%, 99%. So that means you have to you have 1% to the tails, 1% to the tails, and so what would be the on each side? 1% on each tail, so 0.5%, 0.5% on each tail. 0.5% on each tail. So yeah, 0.5%. That would be equal. Oh, wow, why is it? What's going on? 0.5%. That would be equal to, yeah. Okay, that's 0.5 divided by 100. Do that. 0.5 divided 100. 0.05, 2 zeros. 0.05. It's really good that we do have that. We have that on the t-hat. And we want the cutoff. We do have that. Is the last 0.005 here. And the degree freedom, what is the degrees freedom? 18. Here, 2.878. 2.878. The cutoff is 2. T 2.878. That is the cutoff you want. And the confidence interval, 99% confidence interval will be in the middle. The middle 99%. That is what you are looking for. So it's a follow so the slope would follow a t distribution. And then how would you find the right answer? 2.878 is basically between these two guys, between D and E. These two guys will give you the 27.867. Oh, there's another one. Oh yes, E is good one. E or C, both of these would give you the right cutoff. Now, how would you find the standard deviation? Standard deviation. Standard deviation. Standard deviation, now you have a sample size equals to 20. So you'll be looking for this kind of guys. Standard error of coefficient. Yeah. So you'll be looking for this guy. So here's a standard error of the coefficient. This one. So you would be looking at this one. Then found it. Basically, it's here. 2.878 times the standard error. Here's a estimated standard deviation. It's this one. Let's see. Let's check. Yeah, let's go back to yeah, good. Let's see. This question basically you just need to read the table, standard error. This is the standard deviation. Standard deviation, when you have to estimate it, you have a standard error. Number three, number three is a really good question. In tossing a fair coin, which of the following sequence is most likely to more likely to occur? Hmm. Uh, Basically, you're tossing a fair coin. Which one of the following is more likely to occur? They're all equally likely. Yeah, if you're kind of tossing a coin, basically, coin toss is really independent. Independent means that, yeah, it has no memory. The first toss does have no influence on the second. And the first and second have no influence on the third. It doesn't matter. There's no particular pattern. They're all equally likely. Uh, More likely to occur. Yeah, I'm kind of confused about this one. So number three. Number three says A. A is yeah, A says this one is more likely to occur. But I'm not sure about this one. Yeah, let me check. Let me check. Uh, I don't have the right answer. Look at number two, number four. There has been a growing number of news stories about white American calling the police on people of color whose behavior is completely normal. Yeah, that makes sense. Sometimes that happens. A criminologist hypothesized that the mean number of such incidents in the country, two per day. A sociologist believes that two means greater than two per day and plans a hypothesis test at 5% significance level, 5% on a random sample of 50 days. Random sample 50 days. For which of the following possible true values of mu will the power be that has greatest? Let me copy this one. Yeah, so normally we know it's normally distributed. The mean number is two per day. The predicted mean, and a sociologist true mean is greater than two per day, and he wants to do a hypothesis testing. For which of the possible true values of mu will be the power be the greatest? The power two per day. The true population mu. Uh, two per day. So basically, you want to figure out what is the research hypothesis, what is null hypothesis, or what is the alternative hypothesis versus the null hypothesis. The null hypothesis is mu equals to 2. The alternate hypothesis says the mu is not 2, not equal. Here, is this directional? It means greater, so it means greater than 2. The mean is greater than 2. What is the power? The power is your ability to reject null hypothesis. When the null hypothesis is false, when the null hypothesis is false, and so you see that which one is further from 2. Let's see the, so we just got 1.5 minus 2, what's the difference? 0.5 negative. Let's do this here. So the first choice is 1.5. So the difference, what's the difference? Negative, well, we can call it deviation, 0.5. And here what's the deviation? Negative 0.15. And how about the second one? Second one, the true mean is 0. So there's no difference, no difference. Here, for this one, it's a positive 0.15. 2.4, that is a 2.4 minus 2, that's a 0.4. You look for the greatest difference, the largest difference. The largest difference power seems to be the largest difference of power seems to be this one. 0.5. 0.5 is larger than the deviation is the absolute value is larger than 0.4. But we are doing a one-tailed test. We are doing not a two-tailed test. We care about the positive differences. We care only about the positive differences. Among the positive differences, this one. This one is the largest deviation. So I'm betting on this one. I'm betting on E. Let's check. Yeah, it is one. So we don't care. Although the tricky part, you see, negative 0.5 is further away from the true, from the observation, right? But the problem is the prediction. You are predicting that it's greater than 2. So don't care about the other side. You don't care when the true value is lower. Actually, 1.5 is lower than the prediction. Number 4 is good. Mm-hmm. 6, number 6. Let's see. Oh, number 5, a simple random sample. Let's see here. Mhm. A simple random sample is defined as number 5 by the method of selection. How representative is here defined by method of selection. How representative the sample is of the population. Whether or not a random number generator is used. Yeah, this one is not good. You don't have to use a random number generator. There are other ways to get random numbers. Assign different numbers associated with outcomes and chance situation. Which of the outcomes? Yeah, so a simple random sample is the method of selection. It's basically the method of how you select the sample. Uh, Whether non-random, assign different numbers, associated outcomes, and chance situation. Examination. Yeah, I'm betting on A. Let's check. Number 5. Yeah, it's just the methodology. How you sample. Basically, it's how you select the sample would determine whether you have a simple random sample or not. Let's see. Number 6, can shoe size be predicted from height? Random sample 50 teenagers. The standard deviation in height was. Now you have a standard deviation, but the standard deviation shoe size was 2.3. The least square regression equation is here. Predicted shoe size. This will be the intercept, the slope. What was the R, the correlation coefficient? Yeah, that's a really interesting question. Shoe size. You have a random sample, so n would be equals to 50. Standard deviation, you have the standard deviation of height and the standard deviation of shoe size coming from the 50 people. And you have this regression formula. What is R value? Yeah, what would be the R value here? There's not enough information. Yeah, basically you have the A and B. Let's look at this one. Yeah, you have this. You have to use this formula. That's really tedious. Yeah. Formula. Yeah. have to use this guy. D, that is a slope equals to what is the sum of standard deviation of S? So S sub y divided by S sub x. Yeah, this is a formula for getting B. And your time is with R. The correlation that's where the correlation coefficient comes from. Yeah. You have 50 teenagers. The standard deviation of height, 84, 87, and the standard deviation of shoe size. So the standard deviation of a shoe size is 2.3. Here the B is a 0. Basically here 0.25. This is B equals to R times predicted shoe size. Shoe size is a predicted variable. So shoe size here 2.3. 2.3 divided by 8.7. 8.7. And this is how you get the R value. So the R value, if you want to convert it, R value would be, you still have 2 point, you have 0.25 times. Now you move this part to the left, to the other side. And that'll be 8.7 divided by 2.3. 0.5 times, so 0.5, that's a beta times, this will be a height divided by 2.3. Yeah, it's A is good answer. This kind is key. Yeah. Let's look at this probability value again, see how we figure this out. Question 3. How we figure out this probability. Basically, you're tossing a fair coin. Which one of the following sequences would be a most likely? It's too much. It's just printed. Yeah, let's see how do we do this. Get rid of all the other irrelevant ones. Focus on number 3. 1, 2, we put it here. Yeah, number 3 is here. All right, so have all these sequences, like what work out A. What would be the probability? Yeah, if Faircorn had uh, right. So let's see. What is the likelihood of this one? A. For the first one, first trial had 0.5. For the second one, still had, you have a 50% chance. For trial number 3, you have 50% chance. How many trials? 1, 2, 3, 4, 5, 5 trials. So basically, is 0.5 to the power of 5. You multiplied 5 times. For B, 1, 2, 3, 4, 5. So you have 6 trials. There are 6 trials. So 5 to the power 0.5 to the power 7. Oh, this is a tricky question. That's where it comes from. And for C, you have even more trials. You have, no, here's a 6. You have 6 trials. And you have 7 trials for C. The smaller the number of trials, the smaller this guy, the exponent, and the larger the value. So A has a biggest likelihood. And if we want to calculate the specific value, we can use a calculator. Yeah, this is a tricky question. Maybe I'll calculate that. Oh yeah. 0.5. 0. No, we clear this one. 0.5. So, that's a square root. 0.5 times, yeah, basically the more time you multiply it by 0.5, the smaller the number gets. That's why A is good answer. Good. Let's look at number 7, 9. A researcher would like to know the new oral diabetes medication help control blood sugar level better than insulin injection. So she's comparing these two. She plans to run a hypothesis test at 5% level significant. What would be a type 1 error? Type 1 error. Type 1 error? It's all about the research hypothesis versus no hypothesis. So number 7, let's copy this one. This is some why is getting so small? No, let's do it this way. Okay. Researcher type 1 error. Basically, you need to figure out the research hypothesis versus a no hypothesis. Let me just write it here. Oh. HOHA, alternative versus research hypothesis. No hypothesis, no difference. Research hypothesis that medicine works better than insulin. And type 1 error. What is type 1 error? Type 1 error is that you reject the no hypothesis. You reject the no difference hypothesis when the no hypothesis is true. That is a mistake. Look at this one here. Is this type 1 error? Researcher concludes she has a sufficient evidence her new medication help more than insulin. So this is a decision. Is this decision rejecting the no hypothesis? Yes, it is rejecting the no hypothesis. And her medication really is better than insulin injection. Is she making a mistake? Is she making an error? No. Her medication really is indeed better than the insulin. She's not making an error. She's making a correct decision to reject the no hypothesis. This is not a type 1 error. However, researcher concludes she has sufficient evidence that her new medication helps more than insulin, when in reality, her medication is not better than insulin. That means there's no difference. There's no difference. No difference. If you look at the HO, no difference is true. And she rejects the no hypothesis. This would be a type 1 error. What would be a type 2 error? Type 2 error. Again, you go back to the no hypothesis versus the research hypothesis. The no hypothesis is no difference. Type type 2 error is that when this hypothesis is not true, when there's indeed a difference, but you don't reject the null hypothesis. When there's indeed a difference, your result shows that there's no difference, no real difference. Spring twisting, type 2 error. Look at this one. Researcher concludes that she has sufficient evidence. New medication helps more than insulin. So this would be rejecting the null hypothesis, rejecting the no difference hypothesis. Can't be type 2, cannot be type 2. Type 2 error would start with a statement that there's no evidence or not sufficient evidence to show there's a difference. We don't choose A. How about B? Researcher concludes that she has a sufficient, no, this is obviously wrong, not about type 2. C, researcher concludes, yeah, here this looks better. She does not have sufficient evidence that her new medication helps more than insulin. This part looks good. Her medication really is not better than insulin. This would not be an error. In this case, she would be making the right choice, the right decision. This one's not good. The researcher concludes she does not have sufficient evidence that her medication helps more than insulin. It looks good. When in reality, her medication is better. This is the right choice. This is a mistake, a mismatch between reality and her conclusion. So that's a type 2 error. Good. Looking at number 9. Researcher thinks she can improve her chance running 5 and improve her chance by running 5 identical hypothesis tests, each using different groups of diabetic volunteers, hoping that at least one of the tests will show her new oral diabetes medication helps control blood sugar level better than insulin. What is the probability of committing at least one type 1 error? At least one type 1 error. That's a really a wordy question. At least one. Let's look at what the question says. So she's using 5% significance level. 5% significance level. And she's doing 5 tasks, 5 identical. She's doing the same study 5 times with different people, with different subjects. For one task, for each one task, she has 5% probability of making a type 1 error. If she's doing it 5 times, and then it's to the power of 5, so let's see, at least one type 1 error. She's doing different, hoping at least one of the tests. What is the probability to commit at least one type 1 error? 5 tests. Yeah. At least one type 1 error. Oh, good. This is a probability question. mm, type 1 error is when the null hypothesis is not false, when the null hypothesis is true, and you are rejecting the null hypothesis. So for each one study, you have the probability of 0.05 or at least one type 1 error. At least one type 1 error, that means there might be a 2, 3, or 5, at least one. So you got to look at what do you mean by at least one? So one possibility is one. Uh, yeah, so there some of these are more smarter ways to do that. 95% is not committing. So 95% is this is a complement. Complement. 1 minus 0.05. That is 95%. 95% of times on each trial, you are not committing any. Yeah. And then this one looks the best. This one is that on all of those trials, you are not committing any type 1 error 95% of the times. And you do it 5 times, so it's to the power of 5. And the complement would be at least 1. This is a smart way to solve the problem. Let me check the answer key. So that'd be none, question 9, right? Yeah, question 9 is C. At least 1, right? That's really a clever question. Look at question number 10. Financial analyst determines a yearly research and dividing investment 50 blue chip companies. She knows that distribution is distinctly not bell-shaped, not normal distribution. If the $50 amounts are converted to z-scores, yeah, you want to get a z-score. What can be said about the standard deviation? Standard deviation 50 z-scores. Standard deviation, they are not really normally distributed, not normal distribution. And the standard deviation, it depends on the distribution of raw scores. It's less than the standard deviation of the raw scores. You are converting it to z-scores, right? You are converting to the z-scores. They are greater than the standard deviation of the raw scores. It is equal to the standard deviation, it equals to 1. Z-scores just have a standard deviation equals to 1. All z-scores have standard deviation equal to 1. This is a good answer. Look at 11. A coin is weighed, so the probability of hands is 0.6. 0.6. The coin is tossed 20 times. and the number of heads is noted. This procedure is repeated total 200 times, and the number of heads recorded each time. What kind of a distribution has been simulated? Uh, Probability. Yeah, here's a p. Yeah, probably this is looks good. Sampling distribution, sample proportions, binomial distribution. Yeah, what kind of distribution? What kind of distribution? So it is either head or tail. So it got to be binomial. It got to be binomial. Mm, it's a binomial distribution. N, what is N? N is the number of trials. The coins tossed to 20 times. This procedure is report total 200 times. And the number of heads recorded each time. The coins tossed, right? Yeah. This procedure repeated total 200 times. The number of heads recorded each time. What is the procedure? The procedure is that you toss the coin 200 times. You call the coin 200 times, and you record the number of heads. So maybe the first time the number of head is like 10. The second time you do it 20 times, the number has to be 12. And you repeat this procedure 200 times, and the number of heads recorded each time would be the procedure. Distribution, total 200 times. So the n would be definitely 200. The n would be a 200. The probability value. So basically, while we look at, we need to kind of figure out what is being done here. So try one 20 times. So throw the coin 20 times, and then suppose you get a head count 10, and then you do trial 2, head count equals maybe 12, and trial 3, you throw the coin 20 times, you count the head, maybe it's only 9. How many trials you do? You up to 200, trial to 200. Head count is like 16. It's an extreme case. Basically, you have this multiple trials, 200 trials, and you are plotting the distribution. You are plotting the distribution. Uh, Sampling distribution is a sampling distribution, sample proportions. No, it's not proportion, it's a binomial. It's basically the n. The n is 200 times 200 twice, and the p-value is 0.06. Had 60% had. You know, the binomial, oh, the n number is d. Yeah, the n number is 20. Let me look at the 11. There are two possible outcomes, head and tails. So head and tails, so that's a binomial. The probability had always be 0.6. And we are interested in number of heads. Oh, we are interested in number of heads in 20 tosses. All right, so 20 tosses. Repeating this over and over simulates the resulting binomial. Yeah, oh, so this is repeating this over and over. That's a simulation. Simulation. All right. So the 20 is a total number of trials. A 100 question multiple choice history exam is graded as number correct minus 1/4 times number incorrect. The score can take values from -25 to +100. Suppose the standard deviation for one class result is reported to be negative negative 3.14. What is the proper conclusion? Well, this one is really a tricky question. So standard deviation is a negative 3.14. What kind of standard deviation is that? Standard deviation cannot be positive. Remember how we get the standard deviation? We first square the deviations. Square the deviations, get the sum of square deviations. The variance is based on the sum of square deviations. And then you take the square root of the variance. Yeah, so every time you see these kind of questions, you look for this one. Error was made in calculating the standard deviation because standard deviation cannot be a negative. Look at 13. So you have a 223 senior graduating this year from a high school. 322 plan to go on to college. When the principal asked the AP student to calculate a 95% confidence interval for the proportion of this year's graduates who plan to go to a college, the student says this would be inappropriate. Why? All right. So there's this is number of students. And you can calculate the proportion. You can calculate the proportion. but you cannot do the 95% interval. Would be the case. The independent assumption may be violated. The independent assumption. There's no evidence that data come from normal or nearly normal population. Yeah, randomization was not used. There's a difference between confidence. Yeah, D is obviously not a good answer. Population proportion is known. Uh, the population proportion of the so senior graduating. Right, this one, the last one really makes sense. The population proportion is known. You know the population proportion. The population, what is population? The 420 seniors graduating this year, and the principal is asking about this year's graduates. So you know the population proportion. There's no need to calculate the 95% interval. Again, another tricky question, another trick question. Look at number 13, answer key. Yeah, good. We got that right. Really good questions. Number 14. AB statistics students large high school plan to survey his fellow students with regard to their preference between using laptop versus tablet. Which of the following survey method is unbiased? Unbiased survey method. Students comes to school early. Survey the first 50 students who arrive. No, this one's not good. This one's convenience sample, not really the best. B, students passes a survey card to every student's with instruction to fill out it at home and drop it. No, this would also be a convenient sample. C, students create an online survey and ask everyone to respond. This would be a volunteer response. Volunteer response samples not really good. The students go to all of the high school sports events for a week. Hands off the survey. And this is biased. This is biased. So the good answer is C. None of the sampling method was unbiased. All of them are biased. 15, a random sample 500 students. It was reported that the test grades went up, average with at least 10 points for 70% of students. When usage of cell phone was banned during the school, what was the degree of confidence, margin of error? Was 2.5%. All right, this is a confidence interval question. Confidence interval question. You have a random sample, 500 students, and 70%. 70% is a percentage. 2.5 plus and minus 2.5. So basically, you want the z-score. Do we know the standard deviation? We don't know the standard deviation, so we have to get the standard deviation. Z-score is good. Here, 0.05, that's good. Does this look good? 0.5. Here's a proportion. This one doesn't look good. This one looks better. You have a zero point 0.7 times 0.3. That would give you the standard deviation. Confidence interval. Yeah, this one looks good. 70%, so the upper boundary will be 7.25, and the lower boundary would be the 70% minus the 2.5%. Yeah, this one is how you estimate the standard deviation of the population of the sample means. All right, time's up, guys. So I'm gonna send you guys a recording and follow the recording and instructions and do these questions yourself.
Okay, yeah, sure. Thank you.
Okay, bye bye.
Thank you. Bye.